So, for me as well, great honor and congratulations to the laureates. I guess since the theme, I didn't really realize it when I wrote my talk, but since the theme is time, I guess the connection would be that it's time to think about new ways to approach some of the things we do. And so the title is a bit ominous, Enter the Machines, but the idea is that many of the ways by which we find new things, we discover things in astronomy, cannot work now, or are much more difficult. This is an example of a field of galaxies and stars, all very realistic, as you can see. And the challenge is to find the outlier, the object that's different from all the others. I don't have a lot of time for the talk, so I won't give you a lot of time to look for it, but you should have spotted this star. And you can see that this star is upside down, and we all know that stars shouldn't be upside down. They have a very preferred direction. They should always be pointing up. But this star wasn't. Now imagine that instead of looking at, I don't know, 100 stars and purplish galaxies, you look at 2.5 million spectra of galaxies. So this is much more complex objects, many more of them, and there's no way you can look at all of them and just find the weird ones just by looking at them. So the challenge is to find the unknown unknowns, the objects we didn't know we should be looking for. We want to be able to do it in various parameter spaces, on spectra, on light curves, on time series in general. We want to be able to do it with very large data sets that are very highly dimensional, so complex data sets, but also do it in a reasonable amount of time. This is a good time to quote this sentence I really like by Dave Arnett. We have to work hard in order to get computers to do what we want them to do rather than what we told them to do. So this is what we set up doing in this project. The algorithm we developed, I forgot to mention earlier, this is work done with my students, obviously, with the beginning with Dalia Baron, and I'll show you some more stuff done with Itamar Rice. The algorithm is an unsupervised anomaly detection. I will shortly explain what is unsupervised in a minute. It's very general, so it could be run on very different data sets. It's a fast algorithm. It can be easily parallelized or run on multi-core machines. And at its core, it's using an algorithm called random forest. Briefly, random forest is a very common machine learning algorithm that is supervised. Supervised means that you have some training set, you have some objects for which you know the labels, you know what they are, and you use it to train the algorithm to separate the objects into the different classes. Random forest does this by building classification trees. So you see an example here where you have some sample of galaxies. You see I like spiral galaxies. And the random forest builds trees using the features, using the properties of those galaxies, and trying to create groups that are well separated into the different classes. But random forest is a supervised algorithm. When we look for outliers, when we want to find the objects that are different from the others, we do not have labels. We're looking for the unknowns unknowns. So very short, and I'm not sure that will be enough time to really explain how it works, but I'll be happy to answer any question about this later. What we did is build a set of synthetic objects in addition to our real objects, and train the machine to separate the real data from the synthetic data. And the only difference between the real data and the synthetic data is the fact that the synthetic data does not have covariance between its features. So you can see here an example. This is some example of data that has two features, feature 1 and feature 2, and you see that there are some correlations. And this is the synthetic data we generate that has the same marginal distributions on every feature, but the covariance is lost. There's no more covariance between the two features. And our random forest knows how to separate one from the other. Once we've built that forest, we can then ask about two real objects, how they go through our forest and how similar they are. Basically, our machine can tell us how similar two objects are. And once we have that similarity, we can basically find the outliers by asking what are the objects that are different from all the others. So we define and measure this pairwise distance in the random forest, and the outliers are the ones that are the farthest from most of the objects. Armed with an algorithm, we want to try it on data, and the first data we tried it on is the Sloan Digital Sky Survey, the sample of galaxy spectra. We have 2.5 million spectra to look at, and one of the great advantages of these data is that they've been around for a while. And so many people have already looked at them using different tools and have found many things. So this is a great benchmark for us to see if we can actually recover the same things. In terms of the features, so when we want to classify, we want to give something to a machine learning algorithm, we need to give it some properties to look at. We did the simplest thing we can do, which is use the fluxes at every wavelength of the spectra as the features. So we have a huge amount of features. We have about 15,000 features per object. So 2.5 million objects times 15,000 features. Now let's look at the weirdest galaxies. The question is, what makes a galaxy weird? These are spectra of galaxies, and you can see that they're very different from each other, and they have emission lines and absorption and continua, and these are actually very normal. And we didn't tell the algorithm what it is that makes a galaxy weird, but we did learn by running it. Do you want to try and guess what's the weirdest galaxy in SDSS? This connects very well with the previous talk because the weirdest galaxy is a supernova. And the reason, first of all, the fact that supernovae exist in Sloan spectra is not new. We knew that. It happens that supernovae explode. They're rare, but they happen enough if you look at enough spectra. And so if a supernova exploded once when the galaxy was observed, the supernova light will significantly modify the emission from the galaxy. And since supernovae have very broad lines, they look very not galaxy-like. So in our scheme, the weirdest object was actually a galaxy, and you can see here in black the spectrum, and in purple the best fit model, and the model really struggles to fit the broad features that come from the supernova. We also find things like stars. This is one of the more interesting ones. This is an AMCVN, so it's a very rare type of star. And also some pretty amusing things that can happen. For example, we see a galaxy, we see it has an additional set of emission lines at redshift 0, and when we look at the imaging, we see that we are looking at that galaxy through the haze of planetary nebula in the Milky Way. So this is not very interesting physically, but amusing to see. Other example of such chance alignments you can see here, where the fiber happened to catch two galaxies. You can see here one set of hydrogen and nitrogen 2 lines, and here another one at a different redshift, and also the sulfur 2 lines appear twice. In some cases we find gravitational lenses, galaxy-galaxy lenses. In some other cases, the two sets of lines we find are actually close together, as in this object. But in this object, what's particularly interesting is that the two sets of lines are nearly identical, or identical really. And this is actually not something easy to do on a galactic scale. So I don't know what's going on here, and this is an object we're investigating further. So these are a few examples. Other examples are galaxies that have continua that are different than what you see typically. This is a galaxy that has so much dust in it that it looks basically completely diagonal. I've never seen a galaxy look like that before. In other cases, the continuum looks fine. It's just a red and dead galaxy. But then if you look at the sodium lines, this is a zoom on the sodium lines, they're huge. So for some reason, this galaxy has a lot more sodium absorption than most of its counterparts. Most of the objects we find actually are unusual in their line ratios. So for someone who's seen many galaxy spectra, this will look odd, to others perhaps not, but look at the sulfur 2 lines. They're almost as strong as the H-alpha nitrogen 2 complex, and this is quite unusual. And with most of the objects we find have some kind of abnormal line ratios. Sometimes we find unusual lines, basically similar lines to the lines Avishai mentioned earlier, high ionization lines. We see them in galaxies. These are called coronal lines. You can see iron 7 and 14 and a bunch of others. All those things have been found before. We found more of them, but they have already been found in Sloan and discussed in the literature. This wasn't. This actually took us some time in actually getting Chagai Netzer to help us identify the line. There's a line at 5200 angstroms that's caused by nitrogen 1. And you typically do not see nitrogen-1 in galaxies. Or if you do, it's very weak. And yet we find galaxies where the nitrogen-1 is actually quite strong. Again, I don't want to go too much into the details, but this is not something that has been specifically addressed much before that. Another example is those galaxies called E+A galaxies, which were known. E+A galaxies are galaxies that recently went through a very active star formation that abruptly stopped. So the O and B stars are gone, but the spectrum is completely dominated by A stars. So it basically looks like a huge A star. And you can see here all the, basically the Balmer and metal absorption lines, typical of A stars. But in this specific case and others we found, we also see evidence for AGN activity that's pushing gas out of the galaxy and perhaps basically seeing AGN quenching in action in those objects. And this is in another paper that was, well, I guess will probably be accepted today. It was just resubmitted this morning. So we looked basically at the top 400 outliers because our algorithm just told us this is the score, how weird every object is, and we started looking until we just saw too many, and 400 was a nice round number, and this is a lot of work to go one by one. We found outliers of many different kinds, emission, absorption, continuum. I've shown you many examples. Many of them were previously reported, so our benchmark worked pretty well, but many were actually new, so we've actually found new things, which is nice and actually not completely expected when you look at data that has been looked at so much. We also found 2 new classes, which was a good surprise. And the main question is, why did it work so well? And that brings me back to the question I asked earlier, which is, what makes a galaxy weird? And I guess the better way to phrase that question is to ask what makes the spectrum of a galaxy weird, or even better, what makes the spectrum of a galaxy or a spectrum in general interesting to an astrophysicist, which is really my definition of an outlier. I don't care about the mathematical definition that, by the way, doesn't really exist, but I care about the astrophysical definition of what it is an outlier. What makes an object interesting to me, makes it an interesting discovery and something to look further into. And I think the answer, or at least an important answer, is the covariance. Take a galaxy and put in a strong emission line. Okay, so it has a strong emission line. But put in a strong emission line while another emission line that usually is as strong is much weaker. And then you learn something interesting about the physics of the gas in that galaxy. So the covariance, how the different features talk to each other, is really where the physics is hiding. And by building a machine and training it to separate real objects from synthetic ones, by stripping the covariance, I think that's what made this algorithm so successful in identifying interesting spectra. So obviously after this, we've had many ideas and we're still thinking about others. One thing is to study further the galaxies we found, and this is work in progress, and as I told you, there's already a paper on that. We're working on improving the algorithm, and I'll give you a short example about this in a minute. We're also looking at more galaxies, because we only looked at 400, but perhaps galaxy 401 or 402 is the one that will make us famous. We're thinking about applying it to other data sets, and we're actually applying it to other data sets. One is to more galaxy spectra. Sloan 4 MANGA has integral field spectroscopy of galaxies. So galaxies, now we're looking for outliers, not just as outlying galaxies, but outlying regions of galaxies. And we have collaborators, we are external collaborators on this, and we already actually found, by the way, a supernova. This is the first, again, the first outlier found in MANGA was a supernova discovered by our collaborators on this. We're looking at stellar spectra. The Apogee survey has about 200,000 stars in the infrared. I'll show you something from that in a minute. We're also thinking about how to expand and move from spectroscopy, where we've been successful, into other domains, most interestingly, time series. It's a difficult and not trivial question of how to import or export our method from spectroscopy to time series, but we are spending some time to think about this. And two obvious things to do how to look at light curves from Ogle from Andre's very, very successful survey with an amazing sample of variable stars, and also the Palomar transient factory with many transients. Again, it would be interesting to find which are the most interesting ones or unusual ones in those data. But also other time series, you could potentially look at astrometry, the positions of stars as a function of time from Gaia, and find objects that move in a weird way. I don't know what we'll find, but that's the whole point. And also we're thinking about applying it to the stream from LIGO to gravitational wave detection streams. Again, apply machine learning, apply an unsupervised approach to see what it is we can find in those data. So one thing I wanted to add and show you is basically what we're doing currently with the apogee spectra and our ways to improve the algorithm. And one of the questions we had is, with the galaxies we looked at 400. Why 400? How do you define how many objects you should look at? And what we did with the apogee spectra is use an algorithm called t-SNE. t-SNE stands for T-distributed stochastic neighbor embedding. The fancy name basically means that it takes a high dimensional space or high-dimensional distances and folds it into a 2- or 3-dimensional space. So we have these, we've run our algorithm on the apogee spectra. We know we have a distance between all the apogee stars, but these distances are in a very highly dimensional space. We can shove it down in 2 dimensions, and this is what you see on this plot. And you get this very weird shape. Each one of us has his own interpretation of what it is we're seeing here. To me, this is very obviously an eye and a pipe, and this guy is smoking, but that could be my bias. The color of the points is the outlier score. So you can see in red the most outlying objects, and you can see that they come in groups in different places. And as the colors go bluer and bluer, you get to the more normal objects, and you see that there's a lot of structure here. So you don't have to only look at the outliers, you can also ask what this cluster is, and what this is, and what these are. Going back to the question of how many we should look at, you can also see that the big clusters have edges that are sort of cyan. This is pretty much where things stop becoming interesting. When you start getting to the edges of the normal population, this is where you want to stop. So you can just define outliers as objects that are outside this cyan color, and that'll tell you which are the ones you should look at. Also, when you look at them, you don't have to look at them one by one sequentially as we did before, but you can actually, if you look at one object here, then you know that all the objects that are in this area will look the same, so you don't need to look at them again. So we can very easily map the different kinds of the different kinds of outliers and found the ones that are interesting and quickly zoom in on the good ones. These are the same maps I showed you before, but this time colored by the pipeline, by the apogee pipeline derived values. So you can see basically the effective temperature here. You can see from I think the hottest stars to the coolest ones. You can see the metallicity. These are the metal poor stars cluster here for some reason. And here the log G. So these tools allow us to dig deeper into the data and find the more interesting things. There are things you can do as well. First of all, if you have a galaxy and you want to know how weird it is, you can just go and check online. We have the weirdness score for every galaxy in SDSS. If you have interesting data that you want to look at with our tool, you can again go online and download it because it's open source and you can run it. Obviously, the devil's in the details, and it's not very easy to apply an algorithm you don't know intimately on new data. So we're always happy to collaborate and munch at your data. And I think that's it. Thank you.